Okay, so from last class, we were looking at this graph, which is called the heating curve, which shows what happens to a substance as it's heated, starting at a solid and ending as a gas. So when we look at this curve, we know that when we have a slanted line, a line with a slope, that means we have a single state of matter that is being heated up. Right here, that would be solid. This green line would be a liquid being heated up, and this red line up here would be a gas being heated up. We also know that we have flat areas of this curve where we have a change in state. So if I take this solid for this substance and heat it up from 0 degrees, when it hits 20 degrees, that's its melting point. So the temperature stops changing and the substance changes from a solid to a liquid. Once the entire sample is a liquid, then it will heat up, and I just continue heating the liquid until it gets to its boiling point, which in this case is 120 degrees Celsius. And then all the liquid will change to a gas. And then once all the liquid is changed to a gas, then I just have gas, and I can continue to heat the gas. So when we look at this graph, we know that heat added at a constant rate is on the x-axis. So what we're going to look at today is how do you figure out how much heat it takes to move from point to point along this graph. So as it turns out, you actually know how to do one of these calculations. You learned about it in the last unit. Because if you remember in the last unit with thermochemistry, we asked questions about, well, if I have a substance at a certain temperature, let's say 60 degrees, and I raise the temperature to 80 degrees, I can calculate the amount of heat that takes using the specific heat equation. So as long as I have a single state of matter and I want to calculate some kind of energy change, I just use the equation Q equals mCp delta T. If you remember, Q is heat in joules, M is mass, Cp is specific heat, and delta T is the change in temperature. So just to review how you do those type of problems, let's take a look at this problem right here, this very first problem. How much heat is required to raise the temperature of 50 grams of solid iron from 25 degrees Celsius to 85 degrees Celsius? The specific heat of iron is 0.448 joules per gram per degree Celsius. So if I'm going to use the specific heat equation, I know I can say Q equals the mass, which is 50, times the specific heat, which is 0.448, times the temperature change, which is the final temperature, 85.0, minus the initial temperature, which is 25.0. And when I multiply these three numbers together, I get my answer. So we know 85.0 minus 25.0 is 60.0. So if I take 50 times 0.448 times 60, I get 1,344 joules. So that would be how much energy it would take to raise 50 grams of iron from 25 degrees Celsius to 85 degrees Celsius. Now, remember, we have to think about significant figures, since each of the measurements in here, each of the numbers we're multiplying has 3 significant figures. The answer really should be reported as 1,340 joules. So that's a calculation we did in the last unit. You did one of these questions in the when you burned the cheese ball and answered the questions in that lab. So nothing changes there. What is new when we start looking at this heating curve is the fact that we cannot use the specific heat equation when you are melting or freezing. So if I am, let me get my pointer here. So if I'm here at the solid, where a solid's changing to a liquid, there's no temperature change. If I'm here, where a liquid's changing to a gas, there's no temperature change. So you cannot use the specific heat equation. So instead, we have to use a different equation. And that equation is actually easier than the specific heat equation. So what we need to know, depending on what phase change is taking place, is how much heat it takes to either melt or boil a substance. So the amount of heat it takes to melt something is called the heat of fusion, which is abbreviated delta H FUZ. That's heat of fusion, and that's the heat required to melt something. So, and typically the units of this are joules per gram. We also know there's a value, just like there's a value for melting, there's a value for boiling, and that's called the heat of vaporization, which would be abbreviated delta H VAP. That's the heat of vaporization, and that's the amount of heat required to boil something. And again, the units of that are joules per gram. How many joules does it take to melt 1 gram of substance? How many joules does it take to boil 1 gram of substance? So if we want to know the amount of heat required to change a state, in general the equation is Q equals M times the delta H for the phase change. So M, again, Q is still heat, M is mass, and delta H can either be the delta H of fusion if I'm melting something, or the delta H of vaporization if I'm boiling something. So let's take a look at an example problem like that. So if we look at this question, how much heat is required to melt 50 grams of iron if it is at its melting point of 1,535 degrees Celsius. The heat of fusion for iron is 246 joules per gram. So what this question is saying is that for iron, instead of being 20 down here, where's my pointer? So instead of this number being 20, for iron it's 1,535. And because I'm already at that temperature, that means I'm at this end of the flat line. So I just want to know how much energy does it take to get across that flat line and take the solid and change it to liquid. I'm not heating up the solid at all. It's just about ready to melt, but it hasn't started melting yet. And I'm going to stop adding heat as soon as the last little bit of solid has melted. So to do that, all we do is say Q equals the mass, which is 50, times the heat of fusion, which is 246. So that answer is 12,300 joules. So it takes 12,300 joules to melt 50 grams of iron once you get it all the way up to its melting point. So if I'm heating something and it's not changing phase, I just use the specific heat equation. This is my Q equals mCp delta T equation. If I'm changing the phase, but I'm not changing the temperature, you notice there's only one temperature here, 1535, then I say Q equals M times delta H. So the last type of question we can look at, though, is, well, what if we have kind of a combination of things happening? So in this question, I'm taking 50 grams of solid at 25 degrees Celsius, and I want to change it all to liquid at 1,535 degrees Celsius. And you can see these numbers stay the same. The specific heat is that, and the heat of fusion is that. So if we think about what's going on, if we drew a little partial heating curve, oops, I need my pen. We would be starting down here at 25 and heating it up. And we'd heat and heat and heat, and then we get to 1535, and then we get a flat line. So since this curve has two segments to it, so if we look at this curve, we have this segment where the temperature is changing, then we have this segment where the temperature is not changing. That means we need two calculations. Whenever we have a temperature changing segment, that's specific heat. So this part is Q, oops. Q equals mCp delta T. And this part is just Q equals m times delta H. So all we would do is we do one question where we say Q, we're going to do the specific heat one first. I have 50 grams. The specific heat is 4.48. And the temperature change is 1535 minus 25. So if I put those numbers in the calculator, what I get is 33,824. But since I only have three significant figures, I'm going to say 33,800 joules. So what that represents is the amount of heat it takes to take the solid from 25 degrees Celsius to 1535 degrees Celsius. So that is my first calculation. So that's the calculation for the slope part. Now I need a calculation for the flat part. So now I just say Q is equal to 50 times, in this case, the delta H is the delta H of fusion because I'm melting the iron. So that's 246. Not 0.246, that is actually 246. And we figured out last time that that was 12,300 joules. So if I want to know the energy change for the whole thing, so starting, I want to know the energy change starting here and ending all the way up there, I just take those two things and add them together. So 33,800 plus 12,300 equals 56,100 joules. So that would be the total amount of energy to go from 25 degrees Celsius and a solid all the way up to 1,535 degrees Celsius and a liquid.